Binomial probability. And we'll see in a second why we do this in binomial theorem. The first word's probably the giveaway. Right. If you think about it, most probability events you can break down to one of two things. Either it's going to happen or it's not going to happen. So you can always break it down to two things. And of course we know that the two probabilities must always add up to be one. So if we were going to do that, but keep repeating it, if I was to draw a tree diagram, we'd start off and so either A is going to happen or B is going to happen. And let's say the probability of A happening is P and the probability of B happening is Q. So as I say, P plus Q would add up to be 1. But then we repeat the whatever it is. So each one of those would branch off and I'd get, well, AA or AB if the first one was A, or I'd have BA and BB if the first one was B. Now the probability of AA then would be P squared, and whoops, there we go. And then AB would be PQ, BA would also be P times Q, and BB would be Q squared. Now this is where the binomial comes into it, because if you actually look at those terms, what have we got? We've got a P squared, we've got 2PQ, and we've got Q squared. If we were to repeat it again, so if it was AA to start off with, it would go AAA, and so on and so on and so on until we get to the last one, BBB, and the probabilities for each of those. There we go. So then you'll notice, oh, that last one should be Q cubed, misprint there. But you notice we've got P cubed, but then we've got 1, 2, 3 P squared Qs, and we've got 1, 2, 3 PQ squares and the Q cubed, which should be there. So once again, it's that binomial distribution with all the coefficients. Let's do one more. So we start with AAA, AAB, and then we're coming down to BBBBB. And so the probabilities on each of those, if I can squeeze them in there, gets a little bit tight. Now, if you were to go through each of those, you'd find, again, that would match the distribution for the power of 4. So, all right, let's summarise that. If it's one event, that's nice and easy. Probability of A is P, probability of B is Q. Two events, probability of A, P squared. Probability of an A and a B. So I don't care about the order. Then it would be 2PQ and then Q squared. So 3 events. We start with P cubed. Again, not worried about the order. If there's just 2 A's and a B happening, I get 3P squared Q, A and 2B, 3PQ squared, and so on. And in our 4 events, if we were to list those, once again, we see, there we go, 4, 6, 4, what we saw with our binomial coefficients. So, we don't need to draw our tree diagram up. If we know we're going to toss a coin or whatever it happens to be, we're going to repeat it n times, probability of it happening is P, probability of it not happening is Q, then the probability that it will happen exactly K times, and we don't care the order, must be the general term in that binomial theorem. Right? So we'll have NCK, probability of it happening to the power of K, so therefore the probability of it not happening would be N minus K. And so that notation I've used there, X equals K, it's basically saying X will occur exactly K times. All right, so we've got a bag, 30 black balls, 20 white balls. Now, the important thing with this is the probability has to be the same every time we do it. So this must be with replacement. Because if I didn't put the balls back, the probability would change then on each particular drawing. So we're going to pull out 7 balls. Probability that they're all black. Well, using this idea, we'd say, okay, probability, if X is the number of black balls, probability that X is 7 would be 7C7. Probability of it happening to the power of 7, probability of it not happening to the power of 0. Of course, you probably realise that that it would be just 3/5 to the power of 7 for that one. That's what it works out to be. 2,187 on 78,125. So maybe that idea is not that useful for something like all black, because, we know that's going to be 3/5 to the power of 7. But if I said it was just, I only want 4, I don't care the order they come out, so probability there's 4 black balls will be 7C4. Probability of it happening 3/5 to the power of 4. Probability of it not happening 2/5 to the power of 3. Now, the 7C4, what you're basically doing is saying that's the number of ways I could arrange 4 black balls and 3, what was the other colour we got? White. So you think about how many ways could we arrange 4 Bs and 3 Ws. So if it was one of those word problems, and I said, okay, how many ways could we arrange B, 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 W, W, W? How many words could we do? We'd say, oh, well, that's going to be 7 factorial. And then, the repeated letters, well, there's 4 Bs, so that'll be 4 factorial. 3 white, so that is 3 factorial. Well, that is 7C4. Okay. So you can think of it 2 ways. You can think of it like a permutation, like I just did over there, or you can think of it like combination. Either way, it's 7C4 or 7 factorial and 4 factorial. 3 factorial, what does it turn out to be? There's the value in unsimplified form. It's another one of those ones where often that's good enough for an answer because some of these numbers do turn out to be quite large. This one's not too bad, I suppose. Okay, so we've got an election. 30% of voters favoured party A. So at random, we're going to select 5 voters. Probability that 3 of them favoured party A. So X is going to be the number of people favouring party A. So the probability that, well, I wrote it as 3 A's, but X equals 3, 5C3. Probability of 3/10, because 30% to the power of 3, probability of happening. Probability of it not happening, 7/10 to the power of 2. And there it is, unsimplified. And there it is, 1,323 over, 10,000. Majority favour A. Okay. Well, this time I'm saying X is greater than or equal to 3. So I've got to look at the situation where it's 3, 4 or 5. But each one of those, same idea, I'm just talking about those particular general terms in the binomial expansion. So 5C3, 5C4, 5C5, probability of happening to the power of whichever, 3, 4, then 5. Probability of it not happening to 2, 1, and 0. Tidying all that up, we get 4,077. Notice I used the dot multiplication there. Because I didn't have a power on the 7, if I didn't put the dot there, it looked like I was saying 73 to the power of 4. So you could use the dot, or you could use parentheses, or I suppose you could write 7 to the power of 1 if you wanted to do it that way as well. Okay, at most 2 favoured A. So don't forget our basic probability theory, complementary events. We've just worked out majority favour A. Well, what's the other possibility? If it's not the majority favouring A, then at most 2 favoured A. So rather than rework everything, I'll say, oh, hang on. Well, that's got to be 1 minus the probability that majority favoured A, the one that we just worked out. So that makes it a lot easier using that idea. So basic probability ideas we can still use. So here's an HSC one from almost 10 years ago now. Okay, 5 matches on a weekend in a football season. Megan's going to take part in the competition. The rules of the comp: 1 point if she picks more than half of the winning teams for a weekend, 0 points otherwise. Now, the probability that Megan picks a correct team is 2/3. So the first thing we have to work out is the probability that she earns 1 point for a weekend is 0.7901. So in order to get 1 point, she has to pick more than half of the winning teams, and there are 5 matches. So if X is the number of matches picked correctly, we need greater than or equal to 3 to get 1 point. We need majority of teams. And there's 5 matches, so 5C3, 5C4, 5C4, 5, and so on. And there it is, unsimplified. They want it rounded to 4 decimal places. Sure enough, that does work out to be 0.7901. Okay. Hence find the probability that she earns 1 point every week of the 18-week season. Okay. Y is now going to be the number of weeks Megan earns a point. And we've just worked out the probability of that happening. So we want to know when Y is equal to 18. Because she wants to get 1 point every single week. So 18C, 18, if we use our binomial probability idea, probability of it happening, well, we just worked out probability of her getting 1 point is 0.7901. So that's to the power of 18. The other one would be to the power of 0. So 2 decimal places, that's 0.01. Now, probability that she earns at most 16 points. So now we're saying Y is less than or equal to 16. Because at most 16 points. Well, I'm going to use complementary events there, because rather than work out 0, 1, 2, 3, 4, 5, 6, it's going to be a lot easier just to work out 17 or 18. Well, we've already worked out 18. So I only have to work out 17 for this question. So 1 minus 18C, 17, 7901 to the power of 17. So therefore it's 2099 probability of it not happening. Power of 1 minus, well, we know that's 0.01. That turns out to be 0.92 all up. Let's try another one. We've got a large city. 10% of the population has green eyes. Probability 2 randomly chose people have green eyes. Okay, first part of the question is not binomial probability. It's simply saying what's the probability that 2 people have green eyes. So each 10% chance, 0.1 times 0.1, so there's a 0.01 chance that 2 randomly chosen people, have green eyes. Now, probably exactly 2 of a group of 20 randomly chosen people have green eyes. So X is going to be the number of people with green eyes. So we say probability that X is equal to 2. So of the 20, 2 of them we want green eyes. Probability of it happening to the power of 2. Probability of it not happening to the power of 18. And to 3 decimal places they asked for this one, so 0.285. Probability that more than 2 of a group of 20 randomly people. Okay. So we're now saying what's the probability that it's greater than 2? Again, here's the complementary event idea. So 1 minus the probability of less than or equal to 2. This time we only have to work out 3 probabilities, as opposed if I went the other way, I'd have to work out 3, 4, 5, 6 and so on. And that turns out to be 0.32. Okay. So 10 J's on binomial probability.